Hello, I'm Ziad Aad, the chairman of Manipulator team from Alexandria University, and we are here today with our Rover Falak as we get ready for the European Rover Challenge. Our journey began in 2016, founded with a vision to push the boundaries of engineering. MindCloud has spent the last decade proving itself on both national and international stages, from the UGVC competition and the rigorous ERC remote edition. Our adaptability has driven us to compete in diverse challenges, including the Minesweepers competition and the Metal Monster competition. Beyond pure robotics, we are deeply engaged in the broader innovation community, proudly participating in premier national events like the IBDAع Festival held by the Ministry of Youth. Executing at this level demands more than just passion. It requires elite organization, starting from the chairman and two vices, and their job is to manage two sub-teams, the technical sub-team and the non-technical sub-team. The technical sub-team has electrical and mechanical. Electrical has software and hardware. And the non-technical sub-team has PR and media.
Here in MindCloud, we are driven by practical engineering, and we are participating in the Rover Challenge because we want to push our technical limits on such a big stage. Ultimately, we want to put Falak's robot design and autonomous systems to the test against the extreme harsh conditions of the ERC Mars yard. Using this competition as the ultimate proving ground to learn, adapt, and innovate alongside the best minds in the global space robotics community.
Behind every successful rover is a mechanical system designed to survive harsh terrains, carry critical systems, and perform with precision. We are the mechanical sub-team responsible for transforming ideas into fully functional rovers. Our design process began with identifying task requirements and competition limitations. Through research, brainstorming, CAD modeling, and a lot of simulation, prototyping, and testing, we transformed our ideas into Falak. Let's divide Falak into three main parts. First, chassis. The chassis is built from 20 by 20 V-slot aluminum profiles, providing structural rigidity, high strength-to-weight ratio, easy reconfiguration, and efficient housing for batteries and electronics, enabling easy access for maintenance. The second part is suspension system. Falak relies on a rocker bogie suspension system. It consists of two rocker arms, each connected to a wheel and a bogie with two wheels, with a central differential part for passive self-balancing over uneven terrains. The rocker bogie suspension keeps all 6 wheels in continuous contact with the ground, ensuring maximum grip, even weight distribution, and high stability. Finally, the driving system. Falak has 6 DC motors with 23 Nm torque and 120 RPM, each connected to an off-road wheel, providing high traction over slopes and ability to move in harsh conditions.
Building an autonomous rover requires a robust electronic backbone. Our hardware system is engineered to handle complex data and harsh environment seamlessly. Maximize efficiency, we custom design our printed circuit board from scratch using Altium Designer, utilizing a robust 4-layer PCB design, ensure clean signal routing, reliable power handling, and precision engineering across the board. Power starts at our high-capacity battery pack, feeding directly into our custom power distribution board. This PDB safely regulates and delivers stable voltage to every critical subsystem. For intelligence, an NVIDIA Jetson or a Nano service at the brain, processing high-bandwidth data from our LiDAR, cameras, and custom-designed IMU sensor. The Jetson sends commands to our STM microcontrollers, which manage the core low-level control loops and signal our heavy-duty motor drivers to execute precise physical motion. From raw power management to intelligent autonomous control, our hardware system is fully integrated and built to explore, and we are ready for the next mission.
Our Rover software system is divided into 3 main departments: communication, artificial intelligence, and autonomous navigation, all working together to ensure reliable and efficient mission execution. Communication team focuses on maintaining stable and secure connectivity between the rover, the base station, and external interfaces during missions spanning up to a 200-meter radius. To achieve this, we use Zeno as our ROS2 middleware system, enabling lightweight, fast, and dependable data exchange across the entire system. On the AI side, our team develops and integrates advanced computer vision models that enhance the rover's environmental understanding, object detection, and helping the autonomous navigation system. These models help the rover better interpret its surroundings and respond intelligently to dynamic conditions.
The autonomous navigation team is responsible for enabling the rover to safely and efficiently move through complex terrain with minimal operator intervention. Our navigation pipeline follows the perception, planning, and control framework. The perception layer allows the rover to understand both its position and the surrounding environment using sensor fusion, height maps, and obstacle detection systems. Using this information, the planning layer generates the safest and most efficient traversable path, while the control layer ensures smooth and accurate trajectory tracking during motion execution. To coordinate all rover subsystems during autonomous missions, we also implement a behavior tree mission planner that manages task execution and system-level behaviors in a modular and scalable manner.
For our rover mission, we designed a custom quadcopter to serve as the eyes of the rover for area scouting. We selected an X configuration for the frame to ensure high maneuverability and to keep the propellers out of the camera screen. To optimize the strength to weight ratio, we ran a detailed stress analysis using SolidWorks. We integrated weight reduction pockets in low stress areas. This reduced the mass while maintaining the maximum structural strength. Finally, the entire frame is 3D printed using ABS material, allowing our drone to guide our rover safely.
We set up a complete drone simulation and a control pipeline using ArduPilot SITL and Python. First, we installed and configured the ArduPilot simulator. Then we launched the virtual quadcopter environment with a live map and a map proxy console. After that, we connected our Python application to the simulated drone using PyMap Link, establishing real-time map link communication through heartbeat synchronization. We then built a custom UI interface allowing us to send commands like arm, takeoff, land, move the drone in any direction and to any predefined point. Finally, we integrated live telemetry feedback including position and speed monitoring, creating a functional ground control prototype that can later be extended into ROS2 integration and autonomous navigation systems.
Regarding our robotic arm system that consists of 3 degrees of freedom, rotation of the base, elbows, and shoulders, and using our end effector that also consists of 3 degrees of freedom, the end effector can grab, interact with panels, and collect samples. In the design phase, we use SolidWorks software to design and use topology and other tools to ensure the design is lightweighted and cost-effective. In the manufacturing phase, we selected highly durable material that can withstand high stresses like aluminum sheets. To conclude, our robotic arm is suited for harsh environment like a Martian environment.
Our robotic arm is controlled entirely through ROS2. We send goals using either Move It or our custom designed script. A path is then planned, and then commands are sent to our controller, which drives the servos in real time and sends joint state feedbacks at 100 Hz. The system's communication is flexible, supporting both Wi-Fi and wired UART communication, both switchable at launch. We have validated the full pipeline from goal to physical motion. Our next step is integrating camera within the system and driving the arm using camera detected points.
The drill collecting mechanism is designed to handle both drilling and sample collecting at the same time. The drill moves up and down using a lead screw mechanism, allowing it to reach up to 30 cm below the ground. During drilling, the rotating auger carries the sand upward, while the cylinder around it keeps the sample contained while moving up, until it finally reaches the attached container at the top of the cylinder based on the Archimedes screw principle. So instead of drilling first, then collecting separately, the whole process happens together using the same mechanism.